Welcome to this explainer. Okay, today we are embarking on a genuinely incredible journey together. We're starting right here, from the solid ground beneath our feet, and we're going to travel all the way out to the very edge of the universe, literally to infinity. And why? Well, our goal is to unlock the mechanics behind gravitational fields. You know, if you've ever looked up at the night sky and just wondered about the invisible architecture holding this whole cosmos together, you are absolutely in the right place. So, let's just jump right in.
Let's kick things off with a bit of a paradox, a really fun one that's puzzled people for generations. How can the exact same force that locks the massive, incredibly heavy moon in its orbit around our planet also make space station astronauts feel completely, seemingly weightless? I mean, it feels like a massive contradiction, right? How can gravity be this inescapable anchor one moment and then just allow for floating acrobatics the next? To really unravel this, we've got to completely break down how gravity actually operates across space. All right, so let's get into it by defining our core concept here, a gravitational field. It's simply a region of space where any mass experiences a force. Think of it kind of like an invisible web surrounding any object that has mass. And we represent this web using what we call gravitational field lines. The arrows on these lines, they show the direction of the gravitational pull, and how close the lines are to each other tells us the strength of the field. Now, from outside a perfectly uniform sphere, like the Earth, these lines are radial. That means they all converge directly towards the center, exactly as if the Earth's entire mass was just squeezed into a single tiny point right in the very middle. Now, down here on the surface of the Earth, this field is strong, really strong. Specifically, it pulls on every single kilogram of your body with a force of 9.81 newtons. And what's super fascinating here is that this value, 9.81 newtons per kilogram, is entirely equivalent to an acceleration of 9.81 meters per second squared. That's exactly what we experience as the acceleration of freefall. For small changes in height near the Earth's surface, this field strength stays pretty much constant, and that is exactly why everything drops at the same predictable rate when you just let it go. Okay, so this brings us to a really crucial distinction, and honestly, one that trips up a lot of people. We need to talk about the difference between mass and weight. So, here's the key. Your mass is invariant. It is a constant measure of your body's inertia, and it literally won't change unless you start traveling close to the speed of light. But your weight? That's a whole different story. Your weight completely shifts depending on the strength of the gravitational field where you happen to be standing. Let's say you have a mass of 60 kilograms. Your weight on Earth is going to be about 600 newtons. But if you take that exact same 60-kilogram body all the way to the moon, where the gravitational field is much weaker, your weight plummets to just 100 newtons. See, your mass didn't change one bit, but your weight absolutely did. Now, moving beyond our planet's surface, Sir Isaac Newton gave us the master key to calculate this force literally anywhere in the universe. Newton's law of gravitation tells us that the attractive force between any two-point masses is directly proportional to the product of their masses and inversely proportional to the square of their distance. This is the famous inverse square law. Basically, it means if you move just one Earth radius above the surface, the gravitational force doesn't just drop off a little bit, actually it drops to a quarter of its original strength. It falls off fast. So as we zoom out into the solar system, we have to ask an obvious question. If the sun is pulling on all these planets, why don't they just fall right in? Well, this exact same mathematical relationship we just looked at, it acts as the centripetal force required to keep planets constantly turning in their circular orbits. The planet isn't just sitting there in equilibrium, it is constantly changing direction. Essentially, it's falling around the sun. By setting Newton's gravitational force exactly equal to the centripetal force, we unlock the physics of how every single planet and moon stays perfectly on its track. It's like a cosmic balancing act. And wow, this next part brilliantly illustrates the pure elegance of those orbital mechanics. When we compile planetary data from across our entire solar system, this amazing pattern emerges. Johannes Kepler actually noticed this long before Newton even came along. He saw that if you take the square of a planet's orbital period, so the time it takes to go all the way around the sun, and you divide it by the cube of its radius from the sun, you get a constant number. From Mercury all the way out to Pluto, that value is a magical, universal constant of about 2.99 times 10 to the power of negative 25. And Newton's physics later proved exactly why this beautiful mathematical harmony exists. But hey, we don't just observe this math from a distance, we actually use it every single day. We harness this exact orbital physics with our modern communication networks. Take geostationary communication satellites, for instance. By perfectly calculating the radius required to give a satellite an orbital period of exactly 24 hours and placing it in an equatorial orbit moving west to east, it matches the Earth's rotation flawlessly.
To an observer down on the ground, that satellite appears permanently fixed in the exact same spot in the sky. And that is the whole reason our satellite dishes can just point to one unchanging location and stay connected.
Okay, let's switch gears and move to a really fascinating thought experiment to see how this builds our understanding of what astronauts actually experience up there. Imagine, for a second, that you are in an elevator, a lift, and you're holding a Newton balance with a 10-kilogram mass attached. When you're just stationary, it reads 10 g-newtons. Pretty standard. If the lift accelerates upwards, it feels heavier, maybe jumping to 11 g. But imagine the cable completely snaps. As the lift accelerates downwards at the exact speed of gravity, the reading on that balance suddenly becomes 0. If you dropped your pen right then, it wouldn't fall to the floor, it would just hover right next to you. You, the pen, and the mass are all falling at the exact same rate. In that moment, you are experiencing weightlessness. Therefore, we can finally solve that paradox we opened with. The whole idea of zero gravity in space stations? Yeah, it's a total myth. The gravity up there is still very, very strong. I mean, it's the very thing holding the massive station in orbit. What the astronauts are actually experiencing is apparent weightlessness. Just like in our broken lift experiment, the space station and everyone inside it are in a state of continuous freefall around the Earth. True weightlessness? Now that is only physically possible in the complete absence of a gravitational field. And to find that, you'd have to travel to an infinite distance away from all mass in the universe. Good luck with that.
So let's actually do it. Let's conceptually zoom all the way out to infinity. This brings us to a highly counterintuitive but totally vital concept, gravitational potential. This measures the work done per unit mass in bringing a small test mass from infinity, like the absolute edge of the universe, to a specific point in a gravitational field. Think of it as a way of mapping out the invisible energy landscape of space itself.
Now, by definition, the gravitational potential at infinity is exactly 0. Wait, why 0? Well, because gravity is an entirely attractive force. Imagine you are holding a mass out at infinity. As it moves inward toward a planet, the gravitational field just naturally pulls it in. The mass itself does the work. And because it's doing work, as it gets closer and closer, its potential energy has to go down. And obviously, if it starts at 0 and goes down, well,
Yeah, you guessed it. This leads to the absolutely mind-bending conclusion that gravitational potential and gravitational potential energy are universally negative values. In fact, if you look closely at the math, there is a permanent minus sign built right into the equation itself. The energy maxes out at exactly 0 only when you reach that infinite, truly weightless distance away. Anywhere closer to a mass than infinity, you are effectively trapped in a negative energy well. You would literally have to add positive energy, like, say, firing up the thrust of a massive rocket engine, just to climb back up to 0.
So, as we wrap up our journey today, going all the way from the Earth's solid surface out to the infinite 0, it leaves us with a truly profound question. If the kinetic energy of all the stars and galaxies moving around is positive, but the immense sweeping web of gravitational potential energy holding it all together is fundamentally negative, what is the sum total? Could the total energy of our entire universe literally just add up to 0? It's an incredible thought, right? I really hope this explainer has transformed how you look at the invisible forces shaping our reality. Thanks so much for joining me, and as always, keep questioning the universe around you.